It started. She's already
Okay.
said so it started. Yeah.
Good. Good. Good morning, everybody. Good afternoon. Good evening, depending where you are. Special welcome to Bruce, who is in the east side of Canada, and we appreciate not the best time of day for you, but perhaps it could be worse. My name's Neil Phillips. I'm standing in for John Bristow tonight. He may come on later, I'm not sure, but that's why he's asked me if I could get this started and possibly handle the questions at the end. It's a great pleasure to say welcome Bruce. He's actually a graduate of Natal, even though he's working now in Canada, and he's going to talk on a topic tonight. I think you've all seen the sort of fairly detailed summary of what he's done and what he's going to talk about. But this topic of plate reconstruction in the past is one of considerable interest. I'm sure it'll remain considerable interest, and I think it's great that he's coming along with some new ideas and telling us what might have gone on a long, long while ago with the different continents. So I'll hand over to you, Bruce, and say welcome and thanks for putting your time and effort into this talk today.
Thanks very much for the opportunity. Right. We're all accustomed to working with looking at geological maps. Unfortunately, effectively, these are designed to be printed. They're very static views, and we have to mentally unwrap things if we want to have a look at stuff. There's no reason for us to work that way in these days. So I want to share an alternative approach to working with GIS-related digital geological information using Pilbara, Cartval, Zimbabwe as an example, and looking at it in terms of its Archean to Paleoproterozoic evolution. Want to try and create things as a real dynamic view. In order to do so, we obviously have to change from the paradigm of periods and eons, etc., and really start applying numeric ages. We want to be able to move towards a state where we can look at things in ultimately 4 dimensions, X, Y, Z, and time. A lot of things have been done that are moving to 3-dimensional presentations. Well, let's just bring the time component in and let's start creating things that will allow us to look at it that way. It's particularly relevant if we're wanting to compare multiple areas on the Earth, especially ones that are far removed from each other at present day. So using plate reconstructions and models to carry the type of information that we're wanting to look at becomes quite important. I'm going to spend a little bit of time just taking one through what I'm doing and what it's going to look like before actually moving into a whole series of animations that try to illustrate the geology. There are quite a few models out there that we can start thinking of using. Dave Evans and I have been developing one which extends back into the Archean just to try to create some structure. There's a little bit more art the further you get back than there is science in terms of assigning what goes where. But we can create the structure that allows us to work with things, and I'll talk a little bit about why we can do that. Different models have very different levels of detail, and that's been one of the features with our paleoplates model, that we try to have as much detail in terms of the polygons that are going to move around the geodynamic units to allow us to get back into the past. You'll just see the difference in terms of the number of polygons between the paleoplates model in the top left coming down to, for instance, Chris Catiz's paleomap model at the bottom right. Reconstructions done in the young period of time, say less than 170 million years, the oldest preserved oceanic crust, open up a number of other problems or limitations. Far more sparse data. We have problems with determining the longitude, but there are models and ways to approach that. And again, we can structure things. Paleomag obviously is really important, but we can also, to some extent, ignore aspects of that and just look at the relative motion of certain blocks, especially if we're looking at a limited number of blocks, because vergent directions out of structural analysis actually tell us a lot. And we're working on a globe, so things can only move apart a certain distance before they start interfering with other blocks that are also trying to move apart as we move back in time. So we can do a lot and then bring in other levels of information that allow us to constrain things. For today, I want to have a look at the comparison of Karl, Zimbabwe, and Pilbara. So effectively part of Vaalbara as one of the models, uh, taking a variety of geological maps, all essentially at the 1 to 500 to 1 to a million type scale. And that obviously imposes certain limitations on what one can or can't see. But it really isn't too relevant at the scale of trying to do it as an animation, because everything gets very small in any case. I'll take you through a little bit of the methodology, because it's actually surprisingly easy to reorganize existing GIS maps by adding about 5 additional fields to do what I do today. And I'm going to draw from those cratons and the Limpopo belt. I'm going to focus a little bit on the Witwatersrand Basin, uh, on Vaalbara throughout the talk, the Limpopo belt, and then the Bushveld complex, just to highlight some issues that I think one can see and interpret in a slightly different way at times, uh, based on looking at it differently, looking at the data differently. So we'll be looking at the Karl craton subdivided into a number of subdomains, tectonic blocks that we want to move around, the Limpopo belt, the Magondi belt, and the Zimbabwe craton, and then Pilbara, which is subdivided as shown on the right into east and various other components, all of which become tectonic elements or geodynamic units that we can move in paleoreconstruction terms. It's important to define those blocks as best possible based on the geology. And that means one takes geological maps, geophysical data, whatever is available to try and subdivide things. One of the important aspects here, looking at this grayscale error mag image of Southern African Development Community, is that we need to define things not the way most geologists look at things in terms of what's the latest overprint or major tectonic event that defines the polygons we might think of, but rather what's the protolith age, what's the oldest age that goes with particular tectonic elements. And those will then carry the information that we want to carry right the way forward. In addition to the ones I showed on that previous one, obviously Pilbara. So if we want to talk of Vaalbara, then we've got to have Pilbara as part of it. I'll be using the de Kock location, because the Pilbara has been in vastly different locations relative to Karl in some previous reconstructions, from south of the Karl in present-day terms to east of it, and then the de Kock one, which is paleomagnetically constrained, puts it to the northwest. And we also need to think of the Groenhonia craton in Antarctica, which is probably an extension. Unfortunately for Groenhonia, we can only really base the information there on geophysical data. There is one outcrop of Archean material in the Groenhonia. It's about the size of a dining room table, and that is it. The rest is geophysical, and there's some Proterozoic material. To organize all of this, really, ideally one sets up a structure. And what we did as part of some IGCP projects was to create a database for geochronology. That's the date view one. Another one, more importantly, for this StratDB, which allowed one to capture lithostratigraphy, coupled then with geodatabases for the GIS side of things and plate models. The field names that I've got listed here are just some of the ones that are in these data systems that allow one to work with things. And you'll notice that age is a prominent part featuring across all of them, allowing us to work with it through time. We came up with a number of different ways to illustrate things in a very simplified form. One was to couple geodynamic setting with lithology, giving this grid. Another way was just to look at the sedimentary depositional setting together with what is intrusive or extrusive. And that's what I'm going to be using in looking at stuff today. But as part of that, we were able to then also generate correlation charts where on a y-axis you go from older at the bottom to younger at the top, and you have a series of domains. Don't worry that the text is very small. All one wants to get is the concept that one can do this type of thing. One actually uses GIS, as it happens, to produce this. It's not a map, but it is an XY plot space where different colors represent different tectonic settings and rock classes. And exactly the same data, this happens to relate in this case to the area we're interested in, could be recast in terms of that depositional setting. Marine in blue through to fluvial in green, intrusive rocks in red, extrusive rocks in purple. And you can just see that very clearly with this. One can add in other layers of information. This happens to be part of a North American correlation chart, bringing in geochronology, for instance, associated with different domains as a way of just summarizing the information. This is stuff we've done in the past with various publications, but we hadn't really looked at what one can do in terms of geological maps, and that's what I want to concentrate on today. So what we're going to do is to combine the information from 5 geological maps, all symbolized the same way, adding a whole series of additional layers of geological information, and with everything imposed with numeric ages to allow us to work with things in a nice organized sense. The general symbology that will be used throughout this is shown here. Again, metamorphic ages as dots will show up as blue. Extrusive igneous ages will show up as green dots. Intrusive as red. Active faults, and this is the only real interpretive aspect of this active faults in terms of determining their age is very difficult. Extrusive igneous rocks in purple, the polygons from the GIS maps, red for intrusive, fluvial green, marine in blue, getting darker in general with deeper. If one can't distinguish what the nature of the sediments are, then it comes up as a browny peachy color. And then one wants to be able to show things that already exist at the time one's looking at something. So pre-existing crust, stuff that had already formed, is shown in gray. I'll illustrate this a little bit more as we go. So here's an example. It's a time snap at about 3,410. Purple volcanic rocks for happens to be Barberton, that's illustrated here, relative to red intrusive rocks of this sort of age from the ancient gneiss complex on a backdrop of some black lines, which are these tectonic elements, the geodynamic units. Here we go slightly somewhat younger. You can see that those older rocks are now shown as gray. This is the mapped distribution that's available. We're not trying to infer and extrapolate the extent of what might be. We're trying to hold it to the data that is actually available. And marine blue rocks, or dominantly the fig tree. Immediately you start seeing not all of the fig tree is necessarily marine. The scale and what the information that's available, we have to summarize and limit ourselves to some extent. You can see some red dots in there and green dots as well. Here we come up into, happens to be Moody's, dominantly fluvial to deltaic. We call it fluvial in this case, and an inferred active fault with that magenta color. One of the problems with doing this is that what's exposed at surface can be very limited. So ideally one wants to try and fill in the gaps. And there's no good way of doing that at the moment. One of the things I've used is to effectively take isopack maps where available, and this here is one part of the lower Witwatersrand, the West Rand group, dominantly marine, hence it's in blue, pulling out the isopacks to try and give some extent and adding in various other polygons where one might not have isopacks, but at least it's showing that it is all together. If it was fluvial, I'd be using a green color. You'll also see some pink lines, which are dike swarms, picked out at various places. And then the animations are effectively going to be typically presented something looking like this. The main animation, the main reconstruction part is in the center. Because one can't see, things can be spread apart, I'm focusing on the pulver itself in the circle on the top left and the Zimbabwe craton on the top right, just so one can pick out what's happening there while the main focus is on the Carl craton. I'm using G-Plate software, and it's set up so that it mostly set up so that the Carl craton or part of the Carl craton is held in a constant position, just so we're not zooming all over the space and continually having to readjust focus in terms of what the center of an image is. It does cause issues with how one views things in terms of the perspective, but it's the only way we can use the technology at the moment. I'm not going to be adding much new other than a way of showing this and highlighting some of the issues that we possibly need to think about in understanding the geology. There's a huge amount of information behind all of this. There's no chance that I can acknowledge everybody that's provided the data that we're then pulling together to use that. Geological maps, if necessary, taking published information that might not be an actual geological map and then georectifying. The local geology for particular areas, I've tended to focus on certain people's summaries. I've listed those here. The models, effectively, I'm using paleoplates, which is something that David Evans at Yale and I've been working on, using G-Plates as software to facilitate the model representation. A lot of this was driven by some IGCP projects, in particular 509 and 648, that I was quite heavily involved in, and databases which are available online that provide access to the data that I'll be using, and anyone can access DateView and StratDB. The isopacks come from a variety of sources, really useful work by a number of folks. And then the dikes compiled by various maps. And I'm involved with the LIPS consortium that's working on that as well. There are some obvious limitations that come with this. I want to highlight some of those before we get going. Any representation that gets used in this type of thing is only as good as the geological map information. And there's nothing wrong with what folks are doing in mapping, but the way it sometimes gets represented or the level of detail that gets provided can have a big influence. What's at surface versus what's in subcrop can influence things, and one tries to pull that together. The biggest problem with most geological maps is that they don't provide numeric ages. So one often has to add that in the database system. We provided that and link it through to the GIS maps to facilitate that. It's also worth remembering that subsequent deformation will affect the distribution of older units. If we think of the Carl craton, just take the Vredefort impact at about 2 billion years. That produces a very different distribution of rocks for the Witwatersrand, simply because of that massive doming structure. I'm not trying to take that out. I'm using the actual mapped distributions in general, so one has to be aware of those sorts of impacts potentially. We're not trying to extrapolate to where things might have been in general, at least not at this point in time. Trying to show what we've got as hard data that'll allow us to then, in our mind, start extrapolating on. When we're dealing with faults, etc., faults and thrusts. The steep structures are easy to represent. Uh, Low angle thrusts are far more difficult, and you'll see what I've tried to do, not always as successfully as I would like to. If there are spatial variations in the sedimentary nature from one part of a unit to another, unless that's captured in polygons in a GIS data set, one can't show that at the level of detail, and one has to just come up with something that's an approximation that works in generally. There are limitations in terms of the technology. G-Plates doesn't have the symbology capabilities of GIS, and GIS doesn't have the plate reconstruction side of things, where there are commercial packages. They're actually pretty slow to do reconstructions. Things that I can do in G-Plates in, say, 10 minutes would take me a few days in a GIS reconstruction sense. I don't have plate boundaries in the models I'm using here, but you'll see how I get around some of that in visualizing. And then the other thing is when one wants to switch data on and off in the animations, if you had imprecise ages, say plus minus 50 million years, and you try to switch that on based on the uncertainty, it'll stay switched on for a very long time, totally inappropriate for the level of detail. Whereas if you had a very precise something, say plus minus 0.2 million years, and you were stepping every 5 million years, you would never actually see it switch on. So the happy medium I've found is to make all of those appear on for a set number of increments in the model, and I'd ideally screen to primarily use only the precise data, not the very imprecise data. So let's get on to having a look at why. Well, first off, it's a dynamic representation, lots of layers that one can bring in. To my mind, it aids the visual recognition of either inconsistent or consistent patterns. Geologists are very good at spotting patterns. It would be quite easy for geological surveys to add some of this additional information to published GIS maps, and I would encourage that to be done. It's easy to reconstruct correlation charts to go with the animations, and if one really was working with only local situations where you don't really need plate tectonics necessarily, you'd be able to go and use a time slider version in GIS and start achieving much of what I'm going to be showing just without the motion part. Let's start off having a look at the early stages of development, and I'm going to work from old to young as part of this presentation. We'll go straight into an animation. You'll see the age counting down. Activity, in this case, in ancient gneiss complex. You'll see what's happening in the Pilbara in the top left and the Tokwe segment of Zimbabwe in the top right. Various polygons to the right of where the ancient gneiss complex is Grunahonya with its subdivisions. Up towards the top right, you'll be seeing part of the central Limpopo belt. At some point, we have to start believing in plate tectonics or motion. At the same time, lateral motion doesn't necessarily all imply plate tectonics, and Jean Bedard, for instance, talks of snowplow tectonics. That's obviously a relevant way of thinking of things from a Canadian perspective. I guess for folks in South Africa and Australia, grader type tectonics might be more appropriate. So that brings us through those early stages. You can see what was happening in a variety of things. Pilbara is off to the left somewhere. I've got it close enough just to be able to include it in the visualization. I'm not implying that it is this close, but one has to try to make the technology work for one. Coming onto the Witwatersrand and the Pongola basins, I want to make a comment on some aspects of the data that are available, which highlight or reinforce some of the discussion that occurred in a very interesting gold series that OGG sponsored. At the top here are 3 isopack maps for subgroups within the West Rand group, the Lower Witwatersrand, recently published by Nick Bierkes shortly before he unfortunately died. At the bottom are some 1966 isopacks presented by Brock and Pretorius. One wouldn't think that we're talking about the same geology looking at these two. Nick's data control are the black dots shown in there. The majority or the largest number of control points that he has available, I think, is 10, looking at the black dots that he presents. If you look at the images down below, there are a whole series of small black dots, and I'm just going to zoom in on one of those. These supposedly were the control points available to Brock and Pretorius in 1966 at the subgroup level. Nick was a very rigorous researcher, so there's no way he would ignore data. And one's left then to say, well, clearly he wasn't able to access the level of data that Brock and Pretorius had available. So either in some way, we're losing old information. I don't know if it's in archives that we just don't have access to, or if it's physically lost from the discussions in the BITS series, the gold series. It seems that it's a little bit of both. And ideally, we need to do our best to try to recover whatever we can and preserve it. But anyway, let's use what I'm going to use the Brock and Pretoria stuff. I'm going to ignore the thermal tectonic subsidence type approach that they obviously used in defining a basin, just knowing that they need to be truncated by faults, boundary faults, and work with that. So here we're coming through. I'm using the original age of the Dominion at the moment. I need to change that, but I haven't had a chance to do so because of some technical issues with GIS. Coming through into the lower Witwatersrand, and you'll see where activity and igneous activity is happening around and about. One of the things that is a problem with this is that the lower Witwatersrand essentially is relatively fine-grained sediments, deeper marine sediments, one infers. The scenario of illustrating it this way suggests that everything is moving in towards the Witwatersrand and Swaziland terrains. Is that really the case? Does that make sense? Seemingly, I would suggest no. So let's try a different animation where one has the same blocks, but we just fix some other ones, and effectively the Witwatersrand is then in a lower plate setting relative to the Kimberley and Petersburg terrains. And that just seems to make more sense in terms of where the coeval igneous activity is occurring. It's a totally different paradigm to the way that I was brought up thinking of the development of the Kartwal craton, but maybe it's one that we should be thinking of. And as we bring in part of the Limpopo, potentially in this scenario, one can see coming up into the upper Witwatersrand fluvial sediments and through into getting into some of the Ventersdorp related stuff. If we just replay that again, staying with that, I want to focus now on the Ventersdorp side of things. Multiple episodes of Ventersdorp activity. I don't think we can think of these as one plume, other than if we were willing to accept very long-lasting plumes, but rather as a number of very distinct episodes of mafic, dominantly mafic igneous activity with the felsic in places. It brings out the possibility of when collision occurs along the northern boundary of the Kartwal craton and what the role of that might be in terms of the fracturing and the extension to produce some of the Ventersdorp magmatism. You'll have noticed along the way some distinct similarities between the geology of Pilbara and the geology of the Vaalbara Craton. This is just highlighting at one particular point. There are lots of similarities. It doesn't extend back into the Paleoarchean, so somewhat younger than, say, 2800 would be the first time that one can really start talking of Vaalbara. And it's going to end at some point before the bushveld comes in, as you'll see. But there are very distinct similarities in terms of the stratigraphy, which seem quite compelling, but are they spatially unique, or can it really just be that they similar conditions applied in similar situations? Just to make a point with that, if you look at Zimbabwe at the same time, you're also having volcanism, just not in a stratigraphic sense, far more broken up. But is that, for instance, related to subsequent events that break it up? Something we need to continually think about. Moving on to the Limpopo Belt, there are two major categories of model understanding of what suggestion for what happened. One is that Zimbabwe and the central zone of the Limpopo and Vaalbara collided somewhere around 2,700 million years ago, with granulite metamorphism associated with that. And then there's a reactivation with a lot of strike slip motion at about 2,000 million years ago, again with granulite metamorphism. An alternative model suggested by many people is that all of this actually occurred at about 2,000 million, the full-on collision and the strike slip motion. One can create models that would allow one to look at both. There isn't time to show both, but I've got those if people would like to have a look at them. And there's certain things that just visually don't make sense with certain of these scenarios, or make less sense with certain of these scenarios. I'm going to illustrate some of these. I think one of the things that we need to look at as well is we have three components, and potentially we need to think of these as three separate mobile components, not just as a single massive collision. Back to the AeroMag image, there are a couple of fundamental things that, to my mind, are important when working through this. And it comes from political boundaries that get in the way with where one has access and when one had access to geology and etc. The Limpopo Belt has been a focus between Zimbabwe and South Africa. Massive strike slip motion on the northern and southern boundaries of the central zone. Just highlighting a few of those major boundaries or names associated with those boundaries. In particular, I just want to highlight the Thaba-Zimbi Murchison one, as that comes up time and time again through this presentation. The western margin of the Limpopo Belt is effectively a thrust ramp, with the eastern part being thrust over the western part. The other thing that comes out of the AeroMag here is that you can actually track the Limpopo patterns around the Zimbabwe craton up into the Magondi belt. And once again, I'd say, all of these suggestions that there's a Magondi Kais event, that was disproved long ago by Harvey Moon, Richard Armstrong, and others. But it seems to keep coming back in the literature, primarily because of some 2 billion ages in the western Vaalbara craton, which are, to my mind, are all either associated with the Limpopo belt itself, or more particularly with the Bushveld complex. The Kais stuff in the far bottom left of all of this, that's Meso to Paleoproterozoic, but the very young part of Paleoproterozoic. And that certainly influences my thinking in terms of the dynamics, that Magondi to Limpopo potential association. If we look at the geochron and go back to the 1990s, yes, there were two distinct episodes, one about 2 billion, another around about 2.7, and it was fairly simplistic in terms of the data that was available there, that everything seemed to point to something around that 2.7 mark or the 2 billion. But as more data became available, this is just showing data taken out of date view, and you can see the number of dates for metamorphism and crystallization in the legend. But as more data became available, that Archean event stretched out to a much greater duration. So much so that Dirk van Rieenen these days tends to refer to two Archean episodes, two stages of Archean activity in the Limpopo Belt. One coinciding with the original one, around that 2.7 gigayears, and then another one around 2.65 down to, he says 2.62. I would suggest that it probably extends down to about 2.55. And I think that's fundamentally important. Have a look at this animation now. If we bring the central zone in at that 2.7 to produce the southern marginal zone metamorphism, and then we bring Zimbabwe in, you can see how we might actually address those two stages. But at the same time, the some of the activity doesn't make sense with looking at it with this particular scenario, with everything moving towards Kaap Vaal. Once again, I think we should be looking at somewhat different uh, perceptions of what is upper plate and lower plate. And this visualization, to my mind, helps one. Here we still have upper plate is Kaap Vaal as the central zone comes into dock. So central zone would be a lower plate in this scenario. The docking occurs around about that 2.7 mark. You can see faulting activity associated with the Ventersdorp, and then a change of polarity potentially, which explains some of the massive igneous activity one sees in Zimbabwe, leading to that somewhat younger collisional phase. Another granite plume, and I will highlight that in a moment. The Great Dyke, right? So we need to deal with two major granite blooms in Zimbabwe. One for the Wedza Suite, shown here in the top left as a snapshot, and the other, the Chilamanzi and Razi. Razi is into the northern marginal zone of the Limpopo Belt, but effectively Razi and Chilamanzi are the same. It's just different structural levels, as has been described by a number of papers, including Changdat. It's interesting to note that the early precursor, pre-Transvaal basins effectively show sedimentation trends from northeast to southwest. So for instance, the Salati Formation, shown in the middle of the top row with isopachs taken from Button's work, I think it was. When you get younger, the orientation of a lot of these things tends to move towards a more north-south orientation. You can even start to see that in the Black Reef, which is shown in green on the bottom left. And then one has to deal with, you know, large calcareous marine sedimentation not far south of what would be a major collisional zone with granulite metamorphism. Some of these just don't make sense if the Kaap Vaal craton is upper plate throughout the time frame. So just focus on that again. You'll see the snapshots coming on. It happens very quickly. If folks are interested, I can share these animations and one can grab the time slider bar and play with it. Here I've got the Magondi, which then becomes part of the wraparound. And this is coming through now into more of the Transvaal basin and the various lithological units within the Transvaal supergroup as we step on down through time. Here you see far more of that north-south orientation as we get up into the Pretoria group. You'll also see green staying on into the Botswana portion of things, you'll see Pilbara starting to depart. And presumably more associated with, one would get into more of the strike slip in the younger part of this, the wraparound of things around Zimbabwe. This particular animation stops with a green zone switched on in this part of things. This is one of the limitations of the data sets. It stayed on for a really long time because that's actually from a sub-Kalahari map in which the Transvaal succession was only delineated at subgroup level, not at the formation level. So one's not able to switch things on and off at formation level to see the level of detail that one would like to see the way we have in other parts of the geological map. Hence it stays on for a long period of time and frankly just confuses the issue to some extent, but it's real data, so we have to work with that. We're now coming down effectively about to time for the Bushveld complex. So let's move on. Well, sorry, when did Pilbara break off? Well, difficult to say. There are some paleomag constraints. It certainly must be gone by about 2.2. One has to wonder whether major dike swarms like this one for the Havana dike swarm in the western Karpal Craton associated with the Ongeluk Formation volcanics, might this have been some sort of precursor to the breakup? These are things that I think are worth continued investigation, the way folks have already started to do. It's also just worth noting that paleocurrent directions effectively are dominantly from the north and northeast and off the southwestern margin, the Karpal Craton, fairly consistently through, very few trend in other directions. That's consistent with a lot of those isopac type trough illustrations. Here just again emphasized for a number of the formations within the Transvaal supergroup, coming through down into a 2055 reconstruction. In this case, this particular image was part of a reconstruction assuming a 2 billion collision. So you get a sense that you can play the games with two different ways. It's quite easy to set it up to do just those scenarios. The Bushveld complex. Let's have a look at what was happening around that. If we have major strike slip in the Limpopo, there's every reason to believe that the Tarbes-Mbi Murchison lineament fracture system was also reactivated. That's a major boundary to the Bushveld complex, as you would have seen there, switching it on and off in times that are appropriate for that. And it's really interesting, to look at the cross sections ultimately through interpretations of the Bushveld, because in general we get taught that the Bushveld must be plume related. And certainly any of the teaching that I had in my early days as a geologist were the Bushveld is an intracratonic plume related system, totally divorced from any sense of what else was happening dynamically around it. Well, if the Tarbes-Mbi Murchison lineament is being reactivated as part of this, as just shown in this snapshot to emphasize it, then one can start to understand why the Tarbes-Mbi Murchison lineament might have played such a fundamental role as a boundary for different zones within the Bushveld complex and as an input focus, if you will, for the magmas, as suggested in the diagram that Johan Kruger put out in 2005. Other people have reproduced or come up with the same sort of thing in subsequent publications. And I remember Johan talking about this at a Geo Congress or whatever, or some other presentation, probably in the very early 2000s. So it's not just a plume. It has a plume scenario superimposed on a geodynamic context. And I think we need to be thinking more dynamically in much of what we do in terms of geology in general. To complete the evolution of the Kalahari craton, let's just have a look at a final animation. Lower parts of the Waterberg, dike swarms, things are really shutting down with the exception of some sediments off of the western margin and dike swarms, while there's marine influence up in the northeast of the Zimbabwe craton and continued marine influence in the southwest of the Karpal. And then things shut down until we end up with intracratonic alkaline complexes in the Mesoproterozoic and later into the Namakwa belt along the southern margin. As geologists, we're all aware that most geological interpretations tend to be rather equivocal. We seldom have absolute proof one way or another. So alternative visualization methodologies just may help assist us in identifying which of multiple scenarios might be the most appropriate. It is really quite easy to implement this, but it does require a change in the paradigm for publication of geological maps. And I would encourage any folks associated with geological surveys to try and promote that with the GIS maps that are being published. There are obviously some issues that we need to be thinking of. What drives some of the compression and extension events that we see superimposed on what otherwise looked to have been fairly innocuous periods of time? What other blocks, tectonic elements, do we need to incorporate to achieve internal consistency with the available geology? What other layers of information beyond any of the ones that I've utilized here might help us to visualize things better? Obviously, refine the layers that one is using. And I must admit that I wish I was a young geologist starting out. Given the technology and the data sets that are becoming available, it should be really exciting times going forward. I'll leave it at that. Thank you very much. Open to any questions.
Right, there's some good applause in there. There's Catherine. You can unmute yourself if you have a question.
Okay, I have unmuted myself. Can you hear me?
Yes, we can.
Okay. Yeah, I just wanted to say to Bruce that something you might consider is looking at satellite imagery and not in the conventional way of looking at satellite imagery, but looking at it at a very large scale and looking at the contrast in mineralogical response, which is something that I've done. And although it gives you the current day sort of picture of the Earth's crust, there is a lot of information to be gotten from that that can contribute to putting these puzzles together. Yeah, I see that there must have been movement on the Vaalbara craton much, much later that might have had huge impact on some of what you're actually working with and seeing. I mean, for instance, the Venetia, what you call it, kimberlite, is in the middle of the Limpopo belt. And that must have been the result of movement of the crust at 530 million years. So there's a lot of static geology that's taken for granted. And I think that there might have have been a lot more movement than one is realistically understands at this stage.
Thanks. I certainly agree that we need to have a look at younger events as well. And definitely mineralization. I haven't spoken about too much of that here. It's been a theme of work I've been doing with David Houston and various others in terms of using some of these reconstructions to understand mineralization through time and episodes.
Yeah. Because I've also used G-plates to put all
Yes.
the whole of Africa and East and South America together. And some of the patterns are quite amazing in
Yes,
terms
I
of what
totally
has
agree with
actually
you.
happened. Yeah.
It's one of the reasons that I say it. I think things are going to be quite exciting as one has the data sets to be able to pull and the technology to be able to pull things together. We're going to identify patterns that we might not previously have thought of as being all that important.
Sure, but very
And
interesting. Thanks very much, Bruce. Yeah.
while we're on that about reactivation, a while back I saw a thesis by a student. He was actually looking at environmental stuff and issues in the Karoo sedimentation. And he said he couldn't understand why he was seeing certain patterns which happened to be in the Free State. And I looked at his maps and that looks to be exactly where the De Bron Horst is. So clearly there's reactivation on some of the faults associated with the De Bron Horst right the way through into Karoo times that he was picking up in terms of sedimentology and other environmental and depositional issues. Yes, we definitely need to look at younger times as well.
Thanks.
Okay, if anybody else has got questions, just perhaps mention it in the chat. I'd just like to say, Bruce, overall, that was fantastic. Thank you. I mean, you covered a huge amount of time that way. And I think one of the things that really surprised me was your comment about Brocken Pretorius. I couldn't believe that we knew we had so much more access 50 years ago than has been preserved today. So it does highlight that issue of lost data, but we'll just tuck that away for another time.
Yeah, I was astounded by that.
Oh, it's just incredible, yeah. And Nick Bucas isn't going to miss a whole lot, as you said.
He definitely wouldn't.
A question, and it might be on the scale that doesn't answer very well, but Lawrence Robb and others talked about different granites, Swazian granites and Randian granites, and the boundary roughly in the area of Witwatersrand. Is that the sort of thing that picks up and shows? Maybe I missed it with as we slid through.
Yeah. As I said, it is very difficult to visualize this jumping through as rapidly as I have to with these animations. I know that I tend to, well, I'm going to see if I can jump through. Here I've just got an animation, one of the full animations just in other software where literally to be able to use the slider and just run backwards and forwards, looking at things for oneself. Ultimately, that's the way one has to approach these animations. Or you do it in G-plates itself, because G-plates is what I use, and I create a whole series of every 1 million year snapshots, which I then stitch together for the animation. So one could do it in that as well, and it's responsive enough that you can see it all come together. But that's the only way I find to actually visualize things and focus one's attention on particular time frames that one might like to. I don't think there are necessarily Randian and Swazian granites per se. Yes, there are certain intervals of time where one had far more igneous activity than others. It's sort of quieter periods and more intense periods, and a lot of it relates to sort of supercontinentality or supercraton activity. But once you put the numeric ages on, you'll see there's a spatial distribution, certain things happening, yeah, down in the Swazian to start off with, moving up into the northern part of the Kartval craton along that eastern margin, because that's where exposure is. At the same time, one's getting stuff in towards the center of the craton, as exposed in Vredefort and around the Wits Basin. But to see those patterns, you have to play with the data in this numeric sense.
Okay, yeah, understood. We've suddenly had a whole series of questions, so I'm going to go to Steve McCourt just to answer an explanation of terminology, and then Julian Verncombe, and then Gillian Fulgham. So,
Sure.
Steve, did you want to say anything about your craton terminology?
It's just a little bit of a misnomer to call cratonic blocks which are older than the Mesoproterozoic the Kalahari craton. The term Kalahari craton was introduced by Chris Hartnady and Pete Joubert back in 1985, and it was specifically defined as the cratonic block which was a product of Mesoproterozoic orogeny. So when you added the Natal Namakwa belt to the eastern, southern, and western margins of the older blocks, that became the Kalahari craton. I know there's not a convenient prior alternative name, but there are names like Azanian craton have been suggested, or Southern African craton. But it seems to be something that comes out of North America through ENDL, that you've got to call everything that's post Cap Vaal Kalahari, and it's incorrect. And I think it's just fair to the people, you know, the original work that we recognize that point. But other than that,
point well made.
Thank you. Can I move on to next question? Julian Ferncombe had a comment about ages and timing. Maybe he hasn't got a microphone.
Yeah. Can you hear me?
Yeah, yes, I can hear you. Yes.
I suppose, I mean, I have to own up that this is all work done 30, 40 years ago. But I suppose when we were looking at the Limpopo belt, the geophysics that was available seemed to show that the central zone was the highest unit, and with no proof except sort of field relations and patterns, and specifically things like saying that the thrusts in the vicinity of Renko are thrusting out from the central zone. I would ask, is it possible that Zimbabwe docked with the Kaap Vaal before the central zone collision? So it's not Kaap Vaal central zone Zimbabwe, but it's Kaap Vaal Zimbabwe and then central zone indenting, like the Karakora mark that we'd see going through Pakistan at the moment.
That is certainly one of the scenarios that folks do have considered, and it goes with the classic view of a collision at about 2.7. The problem is that how do you explain the younger collision, the younger geochronology that's still Archean? I'm not talking of the 2 billion. The southern marginal zone, in terms of the metamorphism there, that really consistently needs a roughly 2.7 event. And the direction of motion is from northeast to southwest for that. So one needs some mechanism that drives that. Beyond that, you've got to explain those granite blooms, because if you have massive granite intrusive activity at 2.68 and 2.63, how do you actually produce a really rigid block to act as an indenter at 2.7 when none of that's really formed yet? That's one of the problems I have, and why I'm trying to illustrate this and say let's have a little bit more of a look at this and try to come up with scenarios that allow one to explain everything.
Okay. I suppose I would just go back to the geophysics that seems to show that Zimbabwe and the Kaap Vaal were together when along came this indenter.
Well, I don't know that it necessarily does show that as being together. It certainly shows a flower type structure, but how much of that is due to what happens at 2 billion as part of a younger transposition, thrusting? It's the Limpopo belt is very difficult to interpret. I'm showing one scenario here. It's not to say that this is the only one that I've considered. We can create other alternative scenarios and try and you can create animations that would allow you to say, okay, what if this was a scenario? What does it look like? And does the rest of the allied geology fit consistently? I think that folks who are absolutely focused on the Limpopo belt, for example, could be taking this and trying to unpack it all. What really makes sense with the level of detailed knowledge that individuals have, rather than the overall summarized knowledge that someone like myself has.
I think we might
I mean,
move on.
it hangs on detail. Can I ask a completely different question? How does the Mosquito Creek Basin fit in? Because if you follow through a concept that the Pilbara is linked to the Carp Vaal, the Mosquito Creek is then the Witwatersrand.
Right. The issue here becomes, when might one have formed Vaalbara? When were they in close enough proximity to be thinking of them as direct correlates versus just coeval activity?
Yeah.
And somewhere around Witwatersrand time seemingly is where the paleomag seems to suggest that they come together, very roughly around about that time. It's not well constrained. So it's difficult to say that that Mosquito Creek would be a direct equivalent of the Witwatersrand. On top of which,
I mean, they're similar lithologies, but
yeah, but the whole
I mean,
debate.
I've seen both, and I wouldn't be claiming that they were the same.
Yeah, yeah, not necessarily so. And to my mind, we also get very confused by what is the sedimentology associated with these different basins. And from a Wits perspective, we far too frequently look at gold grades and trends, etc., and impose a sedimentological perspective on that, on the basin. Whereas if that gold is post-genetic, then it's really not directly related to the sedimentology. And I would love to see someone really pull out all the sedimentology for the Witwatersrand as an independent set of data, independent of any of the gold grade related stuff and all of the interpretations that went with that. Then I think we can start talking of what makes sense in terms of sedimentology, the dynamics, the geodynamics that go with where we need highlands to produce sediment sources and where we need basins to deposit it all. What are the processes that go with that? And step on beyond that.
I can't help smiling at those last comments, but as chairman, I'm supposed to be impartial. There's a huge amount there that we'll tackle in our next gold series, but a lot of good stuff to talk about. Toffee had a question. Are we doing enough new geochronology currently across Africa?
Is one ever doing enough geochronology?
Maybe it was a rhetorical question. I'm not sure.
Yeah. Look, I think we're doing as much as we can with funding, etc., and with the people resources. I would suggest that one of the more debatable issues would be, are we actually teaching all of our young geologists the subtleties of interpreting some of the geochron and getting the quality of data that ideally we could get or would like to get to answer the questions we need to answer. And frankly, if I look at some of what comes out at conferences and some publications, I would have to say that we're not always doing the best in terms of interpretation. Folks are tending to use, in many cases, a detrital type perspective paradigm in terms of interpreting igneous data, and they're not thinking of the consequences of some of those interpretations. I mean, one example here is that you end up with, say, two events not too far apart, and all your data in the Discordia sense on a Concordia diagram would plot close to, potentially even within error of Concordia. And one has people saying, oh, there's continuous igneous activity all the way down between, for argument's sake, let's say 2.9 and 2.7. Well, it's not actually that. There was something at 2.9. There's another event of whatever sort at 2.7. And you can't distinguish it from Concordia because that's our analytical precision. But it it frequently doesn't make sense to say we've got continuous activity. It makes more sense to say we've got two episodes. We need better. We've got certain technologies. Obviously, ICP-MS is very important nowadays, with a lot more people have access to that. It is cheaper, but the precision is not as good as some of the TIMs, especially chemical abrasion TIMs nowadays. It's not as good as shrimp in the sense that you're burrowing through your crystals, where shrimp, what you see in your crystal is what you're trying to date in your spot. It's just easier to interpret that data, even though the precision might be comparable. RD TIMs, again, so few grains get analyzed that is one really getting the full geological story? We need combined studies, and I think we need to have more of those, and hopefully. Okay, let me step off another way. We're producing a lot of data. At no point are we providing that data in formats that really allow us to compile bigger data sets easily. So my inclination would be to say we're not doing enough in the compilation of the data and the structuring of the data to facilitate continued geological investigation. In Australia, you've got this new data system that looks very exciting to have that at a national level in terms of geochronology and geochemistry. I suspect that you're missing some components in that in terms of stratigraphy that would allow you to connect the things together in a more effective way for the long term. But it's a huge step in the right direction, much as we tried to do with StratDB and DateView.
Okay, that's pretty good advice on a lot of our geochronology. So thank you for that detailed answer. I've got a question from Linda. Sedimentary sequences on cratons and blocks. Where are the sediments deposited in the ocean that are closing during collision?
Offshore, obviously.
I'm not sure if Linda's still on.
Yeah. One of the issues here with sediments that get deposited offshore and then get caught up in a closing of basins, in other words, going into subduction zones, presumably there's a substantial amount of subduction erosion. And if we have a look at the general geochron record going back in time, we are missing, and we look at how we think continental crust was produced through time, we're missing substantial proportions of that in terms of the preserved continental crust. So I think there's very substantial recycling of continental crust back into the mantle via a variety of processes. Subduction erosion might be a more important one than we've often allowed for or that we have really thought of. So those sediments might well be just gone.
Okay.
I mean, again, just think of the Andes as a modern scenario where you've got massive, substantial uplift. The majority of the sediments that are being eroded off of the Andes are going into the Pacific Ocean side. They're not going into the interior of South America. And yet South America is not growing outwards dramatically, given that the Andes as a subduction margin has existed for almost 400 million years. That can only, to me, suggest that there is substantial subduction erosion of those sediments entering that trench.
Yeah.
Yes, thank you so much, Bruce. That's very comprehensive. I was just wondering, thank you for this, where, when we see the width of the Transvaal, can they actually, backup basin, can they actually be extension within this? Because we always see how stuff got together, but we know that sometimes there is stuff opening and closing, opening and closing. So
I
just
would
wondering
say
about
very definitely yes. And if we look at any of the modern scenarios with varying, fluctuating steepness of subduction, why would we assume that everything is always compressional just because we've got subduction? We know from modern situations there are extensional episodes, and we need to be thinking of where those might be. The problem is that the timescales to change from compression to extension are short relative to the dating precision that we have, especially as we go back into the Precambrian. So how are we I don't think we're going to identify it in many cases from geochronology. I think we have to go back to the fundamental mapping and try to identify particular features in the geological mapping that will allow us to distinguish extensional versus compressional episodes and try and put together scenarios based on that.
Thank you so much.
Gillian, do you want to ask your question? I'm not, if you're online.
Yeah, I was just wondering why your blocks didn't change shape, Bruce.
Okay. For simplicity, G-plates does allow one to work with deforming plates. And that would be nice to do, but frankly, as we're dealing in the Precambrian and certainly back into the Archean, we have enough problem trying to define these rigid ones in any reasonable sense that to start deforming the margins of those other than as a thought process is a little bit premature in terms of what we can actually do. For those who wish to do that thought process with particular margins and zones, I would encourage them to do that in the Precambrian. Dave Evans and I are at this stage really still trying to just create models that give some structure that are the basis going forward for doing more complex things. I don't know, does that answer?
Yep.
You're saying it's technically very challenging.
Yes.
Right.
At this stage.
Okay.
I guess I would say I completely appreciate that and understand. But you know, if someone has a lifetime of work ahead of them and like improvement of this, I would think that was one of the most important things to do.
Very definitely. There are other things we're showing these as entities. Are we not thinking of where did these entities potentially extend to in the past? Just think of Greater India in a more recent scenario, subducting under Asia. There's a very substantial portion of India that is not captured by the surface delineation of what is the Indian plate. And that would have massive impact. Take this here, the Limpopo approaching, for argument's sake, approaching Karval. Or what happens if there was a substantially extended zone that Limpopo was substantially larger towards the bottom of this image at the moment? Okay, so when was that starting to impinge on Karval? I would suggest that that was actually what was happening for many of these accretionary collisional events, and we're just not aware and allowing for some of the extra space that needs to be incorporated.
Okay.
So if the Limpopo block was much broader, then maybe it didn't collide. Maybe it was always a part of the craton, and it just got squished up.
Okay, no, not potentially part of Zimbabwe, but very definitely not part of Karval. The lead isotope characteristics of Limpopo are dramatically different to those of Karval, very much higher mu, higher uranium lead ratio in the source region, not in the rocks as they are now, but in the protolith than for the Karval. So it's not the same crust that's been reworked. It was tectonically a separate element at some point in the past with a very different Archean, early Archean protolith history.
I guess you could apply that same approach to all of the other blocks and ask the same question of them.
Absolutely. This is really just a step contributing, hopefully, to future people doing more.
Okay, I'm going to move on. Bill, if you want to turn on your microphone, you can. Otherwise, I'll read out your question.
Hi,
How do your
Bruce.
models explain this? Sorry,
yeah.
you go ahead.
Yeah, I was just wondering, if I look at the Bushveld complex, you've got the Villanora limb up at the top along the Palala shear zone, and then you come down through the Platte Reef area, and then at Zebedela, you've got a major movement there along the TML. How do you explain how do your models explain that in terms of a collision? Because I'm hearing you saying the collision started at say 2.7 and was completed by 2.2 billion.
Yes, that one scenario has that collision, or effectively completed by 2.55. But then there is that distinct phase of strike slip motion. Well, yeah, let's call it strike slip motion around about 2 billion. And we've got no idea what's driving that. Why would we have Zimbabwe moving in a sinistral sense relative to Karval at 2 billion with sufficient impetus to have granulite metamorphism in this, again, in the central zone of the Limpopo belt? It's that type of question that I think we need to start having a look at. What is driving some of these? Whatever the case, that is occurring. And that means that we potentially reactivating major lineaments like Tarbes-Zimby Murchison. How much motion actually occurs at particular points in time would be very useful to start quantifying in a better sense than we currently have. I mean, a number of people are suggesting various degrees of motion along some of these. And as long as we've got translithuric fractures we then have pathways that plume-like material can access the shallower levels of the crust, which is what I would see as happening in the case of the Bushveld complex.
Yeah, because the movement along the TML is quite significant. I
Yes.
haven't measured it, but it's a long way.
Yeah,
It's
very
a
much
huge
so.
movement.
At about the same time as the Bushveld was intruding.
Yeah, well, it must be after because it's affected the bushveld itself.
Yes.
Or else the bushveld was intruded along that. But yeah.
Effectively it's happening simultaneously because the end of high-grade metamorphism in the Limpopo belt is around about 2 billion, let's say 2,000 million, where say 2030 might be a better approximation, whereas the bushveld is, let's say 2055, just to use round numbers. But Limpopo is not an event that would have happened at 2030. It would have been a long-term strike-slip motion, which would have occurred before bushveld, during bushveld, and extending to after bushveld intrusion. And that's exactly what we see in the geology, as you're describing.
Mm.
I've got a question for Henny, just administrative one. Henny, I've got 2 or 3 more good questions still. Is our time going okay?
Yeah, we're on an hour and a half. It's you guys that are falling asleep. It's fine.
Okay. I'm going to turn, Richard, you have a question on the geochron. Do you want to take us through that? And after that, Linda.
Hello, Neil. Can you hear me?
I can. You're very faint, but just.
Okay. Well, I just want to say that if you take all the published geochronology on Southern Africa, there's probably an equal amount there which is unpublished. Very good data sitting in people's theses and in industry reports. And a lot of that could really help someone like Bruce to get a much more comprehensive story. And I just want to say thank you, Bruce. I really enjoyed it.
Great, Richard. Good to hear. I didn't actually say it, but I did write in. I don't think that many folks are aware of just how much effort Richard put into dating stuff in Southern Africa, and in particular Southern Africa, off his own bat, really, without direct funding. It was an incredible effort. Thanks very much, Richard. At least some of us realize just how much you did put in on behalf of all of the Southern African community during that period of time.
Oh, it's still fun. I'm still doing some.
Yeah, I know you're still doing so, but yeah.
It sounds like Richard's also given us another message for OGG for our to-do list, which is to get a lot of this hidden stuff out there for everybody to use.
Yeah. Richard, do you have actual suggestions on how one might access some of that crypto data?
I was thinking of asking the South African Journal of Geology if they would accept just a whole lot of tables with data.
Okay.
Without having to ask for full papers.
Yeah. We could ask them, but are you aware that there's a journal called Data that literally does accept tabulated data like you're describing?
Yeah, not really. I haven't really followed that. But I just thought the SA journal would be the most appropriate.
It would be. It would be really nice if we could to do that. Yes.
Linda, you've got a question about the great
yeah dive. Actually I've been at bits now that I match name and voice. I didn't know that was Richard Armstrong, so thank you so much, because the contribution that you have done to South Africa, yes, now I could match. and the contribution to the shrimp development. Thank you so much. So just because I was listening and your question come up, because being in South Africa, I think about this myself. Firstly, is the Tabazimbi, I believe, is still active today. And so it must have been millions of years of activity, or billions. But then I'm also thinking of the Great Dyke, because I don't see that you were actually speaking about this during your Zimbabwe evolution. And since I'm from Italy, I always think of the Great Dyke like the Rhine River Valley, the Graben that you have in Germany, Switzerland, that is all perpendicular to the Alps. That goes north-south, and it's just an opening due to the collision of the Alps. So I always thought maybe the Great Dyke is something like this, but then can this inform on the Limpopo origin? Just putting up for all of you, just a thought of mine. Thank you.
Thanks, Linda. I think one of the fundamental aspects of the Great Dyke to me is that it's the first indication of the Zimbabwe craton really acting as a rigid, brittle block. And yes, it tends to coincide, to my mind, with the latter stages of the Archean collision.
Yeah, it's intriguing, yes. But you're correct. It's already that is behaving like a rigid block is important information.
Yes.
And it's not happening in South Africa.
No.
Tofik, you had a question on the unpublished data with CGS. Do you want to just elaborate on that?
No, thanks, everybody. Greetings. Yeah, no, I was just saying that we've now been trying to get this data portal up and running. I think some of you have maybe seen it, where we basically get all the old maps, new maps, and all the data onto a portal. So that's another option. So what we could do is all of that unpublished data could be loaded onto the CGS portal, and then we can also have it duly referenced, and then obviously maybe assign some citation index to that as well. So that's another option. Thanks.
Thanks.
Okay, thank you. Gillian, I skipped over you and your hobby horse. Do you want to wind up things and say anything on that, or do we take it as read? What would you like?
Well, I've written down my comment, and if I'd be very interested to hear people's opinion of it. You know, it's kind of, I was trying to think of an analogy. It's like I must be in a noir mind frame today, but it's like finding somebody out in the street who's you know, got broken bones and looking very bad, and there's skid marks all around him, and you try to give him some medical attention and attribute his injuries to him having been beaten up. You know, this is like a non sequitur. You know,
Yeah.
Bruce has shown us all these collisions and whatnot, and the chronology of everything, and every time there's a blast of volcanism, that must be a plume. It just seems so incongruous to me.
No, point taken. Yep. I'm going to wind it up there. As Henny said earlier, this is all going to be available to listen again, or bits that you may have missed, and of course communicate with Bruce if that's of value as well.
So
Bruce,
Catherine,
look, thank you
Neil, Catherine just got a nice question there.
Yeah,
Susan.
Susan, yeah, Catherine, whatever. They call me Susan, but anyway. I just wanted to relate to the Zimbabwe craton, where Bruce referred to the western edge, which is curved, and the Magondi belt going into the Limpopo belt. Does that not suggest very large-scale folding with northwest-southeast compression? That's how I see it. So I don't know about the total stability and the total rigidity of that Zimbabwe craton. That's what I'm alluding to.
Yeah.
Anyway,
it could be interpreted that way if that was a very late thing, but ultimately, if you've got an indenter situation with stuff wrapping around, then it's not a northwest southeast compression, but rather that northeast southwest.
Yeah, I mean, that's just what I would have seen, and I
Yeah.
have actually seen some of that, or a lot of that, in my imagery.
Yeah.
Which is
I
from
think
looking at very
one of the
large
things
scale
I would
structures.
one of the things I would like to suggest is it'd be really nice to have some of the folks involved in the Limpopo potentially doing a little bit more work and collaborating with those who've been working primarily in the Magondi, and seeing if what makes sense and what might not.
Okay.
Thank you.
I'd say I might wind it up at that stage. Just before I thank Bruce, a quick plug about something John and I and others, John Bristow and I and others have been talking about. We are going to have another gold series. It's going to start at the start of March next year, and we're just starting to put together a bit of a package of some of the questions that we had after March this year unanswered and needing addressing. So that's all happening. Bruce, thank you very much. You've put a huge amount of work into this. You've covered a lot of time, meaning time taking our questions, but also time in Earth history. And we've really enjoyed it. So thanks very much. And for you, your day in Canada is just starting. For us, the other side of the world, our night's just about to start. So thanks, everyone. And great set of questions and involvement. Bye for now.
Thank you very much, everybody.
Thanks, Bruce. Bye-bye, everybody.